Okay, welcome folks. Oh, so nice to see you for this talk on AWS IoT and industrial automation at Amazon. I am Rudy Chetty, a senior solutions architect. I'm also the official reInvent hype man, so if you've seen the videos, keep watching them. I'll be joined later in the talk by Josh Davis and Cameron Fulford, who are both SDEs for Amazon. Well, let's get started. Let's see what the agenda is about, because you want to figure out when you can take a snooze after this long day. AWS IOT Greengrass, I'm going to touch upon it. This is an advanced level talk, so I'll go into some of the features that we think are relevant for it. We've also got the customers are going to come up here, talk about the palletizer and the edge Workcells. So that's where they'll dive into the weeds and show you some code, get into all the nitty-gritty details that you're yearning to learn about. So AWS IoT Greengrass, as you might know, it's edge computing. So we've taken the AWS IoT core and some of the features, and we've put them on the edge. So you can utilize things like local messaging, execution of local lambda functions, and so forth. But how do you get started? What do you normally do? Well, you set up what we call a Greengrass group. Now, with the group, you can see that you've got the AWS IoT Greengrass core. Now that's where everything is going to go through. So that sets up your base for your group, and then you have devices that are connected. Now you're probably wondering, well, how do I connect these devices? Well, you can use Amazon Free RTOS, the real-time operating system that Amazon offers, or the Amazon flavor. You can use the IoT or AWS SDKs, so software development kits, and you can get going. You can even use the Greengrass Discovery API. So you can make API calls and connect with this Greengrass core, and then even better, you can start sending messages between devices. So say there was a thermostat that registered that the temperature is getting a bit high. It could send a message through the core, go to a fan or an AC unit, and actually turn that on for you. And that's one way where messages between devices can go locally, and they don't have to go up to the cloud. So you've got that edge compute that you're utilizing. Now, how do we actually do the messaging? Well, you start by actually creating your Greengrass core. Now, you can do this via the CLI, so you can see that's a CLI command there. You can do it via the console API. There's various ways that you can do it, and I'm just giving you an example here of one of the commands you can run using the CLI. So you can see we're saying AWS IoT create thing. We're giving it a name, in this case, thingamajig. From there, we actually create keys and certificates that we're going to associate with this device. And what that means is when we want to authenticate to AWS IoT, or AWS IoT Core and Greengrass, we want to actually connect in using these keys so that we're authenticated. And then from there, you can authorize your devices to perform certain functions in AWS's platform. So once we've created the certificates, we can attach them to the thing. You can see we've actually referenced the thing that we created, thingamajig. We've even got the principal that we created just before, and the ARN number, or Amazon Resource Number. And what that is, or Amazon Resource Name, and what that is the unique identifier. So think of it as a UUID, or unique ID. And maybe sometimes the phone rings and then you get a notification to say, turn it off. I mean, that happens too in the local compute. It can happen. And then you create the Greengrass group. So you say AWS Greengrass create group, you give it a name, Greengrass group. And then from there, well, I could keep going and showing you all of them, but for illustration purposes, let's say that we're just going to go to the console and we've created our group, and now we're thinking, well, I want to send those messages, as I mentioned, from the thermostat to the fan. Well, let's set up two thingamajigs, or two things, or devices. Internet of Things, that's what we're setting up here. We'll set up one as a publisher, and then we'll set the other one up as a subscriber. So we'll publish a message, and then the subscriber, if it's subscribed to the relevant topic, it will receive that message. And can anyone guess where we're going through? I mean, if it's edge computing, we're going through the Greengrass core. In this case, I'm giving it the name of Hello World Pub Sub, so publish, subscribe. And when Thingamajig1 publishes the messages to that topic, the subscriber, or Thingamajig2, is actually listening. and then the message gets routed accordingly from one thing to the next. But you're probably wondering how we're using this at Amazon, or how certain teams are using Greengrass at Amazon, and this is where we're getting into it now. So before we do that, we have to define what is a Workcell. Now you can see here we've got an Amazon fulfillment center, we've got some warehouse associates, we've got some robotics going on there, some automation equipment, some boxes being packed on a conveyor belt. And to think about it is we can actually take an atomic unit in that fulfillment center. In this case, a robotics work cell. And we say robotics because it involves some kind of industrial automation. And in this case, it's a robotic arm and maybe the conveyor belt. And that's what a robotics work cell is. And there'll be multiple work cells in this fulfillment center. So, you'll have them spread out and they can operate individually, hence the term atomic. And you're thinking, okay, well, we talked about that. What's the next part? And it's like, well, it's the palletizer. And if that's not clear, that is a pallet, so a wooden pallet that you'd store items on. In this case, we're putting a tote. Now think of a tote as a little bin that you can store items in. So those lovely items that you're going to order for Christmas coming up, you might have taken advantage of Cyber Monday and whatnot. Those items go into the bins and then they get stacked on these pallets. And the reason being is you want to move them either between places in the same fulfillment center, or you want to actually move them between fulfillment centers, or maybe even between a fulfillment center and a sort center. So they have to be stacked. And this is where this particular robotic arm comes into play. It will actually palletize or put all these totes and stack them up. That tote actually should be stacked in the middle there because that's how the robot works, or the robotic arm. But you know what? You want to go into the nitty-gritty details. So I'm going to actually call Josh up now and say, you know what? Let's dive into the palletizer and see what it's about and how it works.
Okay. So as Rudy said, my name is Josh Davis. I'm a software engineer inside of the Amazon Fulfillment Network in a team called Advanced Technologies. And so what we do is we build these work cells, and we transform materials inside of the warehouse that transformation process is a consistent process which is sort of uniform across building types, and so we consolidate that in something that we call a work cell. And so the process in and the process out, it sort of functions as an abstraction, as a function. Probably you're familiar with this, many of you. But better than talking about it, I can show you some video, and we can see one of our work cells working. And so I'll just kind of let you watch it for a moment and get a sense of what's going on. So this is an example of one of our work cells. This work cell largely predates AWS IoT. And so when we first built this, we didn't have IoT as an option. And so we were looking at what do we do for the future now? A few years back, we started thinking about what does the future of our industrial automation look like? And part of that was looking into IoT and other options and saying, is this really a thing? Is this something that we can depend on? Because at the time, all of the documentation was all very consumer focused. It was light bulbs and buttons and very consumer-centric sorts of problem spaces. It didn't really deal with the industrial kinds of environments that we were working in and the same kinds of problems. And so there was a big question mark of whether or not it was possible to even use it. And so you can see here this robot is palletizing totes, which is what it sounds like. They have a conveyor in-feed coming in, bringing totes into the system. It picks it up, it queries software to figure out where am I putting this tote, and then routes it to one of these possible pallet destinations. We determine when it's full, and we have an associate come and remove it, and rinse and repeat. And so the question was, okay, we can see how we can build a light bulb inside of AWS IoT. We see here, okay, maybe build an and-on. By the way, just who has sort of industrial background, is familiar with PLCs, just sort of level setting how much context I should provide here? Okay. Anybody, who knows what an and-on light is? Okay, that's helpful. So you can imagine how an end-on light is a safety light or not a safety light. When something goes wrong, you need to address something inside of the building, inside of the warehouse, your manufacturing facility, whatever it is. You turn on this light, it means come fix this problem. Something is wrong here, and that could be anything to I'm out of paper to this machine broke and stopped working, and just basically means I need help, right? And so I could imagine configuring a light and some SNS topics and going through, possibly, I'll get into some of that, why that might even be hard. But doing something like this was a little bit, at the time, difficult to conceive of. So this talk is, we're gonna go into some detail. It's a 300 level course, and we will cover quite a bit. But the takeaways that we want you to have is what the journey looks like, the processes that we went through, and so how we decompose this problem and went into it. And actually, this Workcell here that we're watching is running on AWS IoT, largely. So, as part of the background, as I said, everything was a light bulb. So, how do we go from a light bulb to a much more interesting problem, which is a Workcell, which is a collection of devices, not just a single device, but that form a single function as a set of devices. So, as I said, we first started looking in, and lots of light bulbs, lots of buttons, but that was sort of a deterrent, to be honest, within our team. We sort of looked and said, I don't know, even if they're saying they can do it, just the lack of documentation made us a little bit nervous. But what did we want to do? We wanted to accomplish something which was make it easier to manage and update our robots, make it easier to manage our fleet, know what's going on within our fleet, and get feedback, and remove some of the problems that we were having. And one of the problems that we were having was, I would venture to say that we had probably 10 or more versions of code running on our PLC across the network at any given time, because we would do an update with a controls engineer on site, and then we would take that update and we would roll it out across the network. And that process would include another controls engineer flying around the country, one or more of them, deploying it somewhere, possibly identifying a new bug because the environment is slightly different. Maybe the floor is slightly unlevel or the lighting is different, and so you're having to adjust a little bit as you go. And so as you go through this deployment process of this standard image, you're actually making changes as they go oftentimes. There's not a great source control process. There are some viable ones, but nothing like what we have in software and what AWS provides us. And so we're thinking, okay, that's a problem. It's difficult to update. People are asking for feature changes like, oh, that light blinks at this refresh rate, but could you change it so it blinks at this refresh rate? To have a controls engineer go on site and do that is tedious and expensive, obviously. So if we can move some of that logic out, it makes it easier. So those are some of the problems we're going to be talking about. So specifically, we're going to be covering the connectivity and integration. So what that really means is just communication to that device. And so that's one set of problems, right? You've probably got an industrial protocol in there. You've got a firewall. We'll go through some of that. The next part is orchestration and control, which is really about the logic. Where does the logic live, the business logic? How much of it lives in the edge in the device? How much of it lives in the PLC, in the firmware layer? How much of it lives in the cloud? And how do you make those decisions even? And then, importantly, in the industrial space, PLC integration. This is not sort of your typical software component, and so some of the limitations and advantages that a PLC provides, we want to make sure that we cover some of those. So this is kind of a summary, simplified reference architecture. We'll kind of keep coming back to this off and on. But at the bottom, we have this protocol conversion. And so that's the part that's going to be handled. That's the logical construct. It's not a component, it's not a product, but it's the logical construct there that's going to be solving the communication problem to the device for us. Up above, we've got this event persistence model. And so at the bottom, we have a problem that our device is primarily fronted by a PLC. A PLC is a programmable logic controller. Think of it as a very simple device which has very relevant industrial use cases in it and is very strong on safety. And we'll talk more about that. But so protocol conversion is saying, okay, I've got some set of devices in the edge here in my Workcell. They speak an industrial protocol. They're not cloud ready. They don't speak MQTT. They don't speak TLS. How do I get that to the cloud? And there's a bunch of ways you can do that. But that's sort of the essence of this problem here is You need something in that layer that can communicate to the device and make it look able to speak to the cloud. In the event persistence layer, you have you have a particular model that your PLCs or your cell follows, and many of them are event-driven. And IoT is largely state-driven, sort of more finite state machines. And so we were curious, could we follow a finite state machine? So let's walk through this. So that's our eventual model. Let's break it down and keep it a little bit more simple. So first of all, we have a light bulb. Okay, this is, if you've done the IoT kind of hello world examples, this is probably not too unfamiliar to you. You've got a light bulb down at the edge. It's MQTT TLS enabled. Sends a message up to IoT. It's received by the broker, routed through the rules engine to a shadow. That message is persisted, so the light bulb may report a state saying the color is now red, and goes into the shadow. You may have a lambda that is subscribed, or a rule rather, that triggers from a change to that shadow or some other event which triggers a lambda. And that lambda may run and say, oh, well, that light bulb is red, but it's 5 p.m. And so since both of those things are true, I'm going to set the desired state within the shadow to blue. The light bulb will query its shadow again and notice that the delta from the difference of the desired and the reported state are different, and converge and say, well, I'm going to change from red to blue. That's sort of a typical simple loop for a hello world light bulb. So what we want to do is walk through this and now do the hello world for an industrial application. So the problem with that light bulb, first of all, is that it doesn't speak. It's an industrial light bulb now, right? It doesn't speak MQTT. It doesn't speak TLS. So it can't speak MQTT out of the box. It speaks some industrial protocol, maybe Modbus or Ethernet IP or OPC UA, or very likely some proprietary protocol, which is either particular to your application or to the device manufacturer itself. And so can't get that to the cloud. Also, not capable of doing TLS, probably too underpowered. It probably doesn't have a certificate or a way to manage the secure handshakes. Not really well designed for that. Because of that, probably, the access to the internet in general is closed off, right? These devices, these industrial devices, you don't really want to expose a big robotic FANUC arm like that to the internet. So they're behind firewalls, they're not accessible. And it's probably, so you've got all these industrial protocols, and it's probably not even a light bulb, it's probably a PLC, right? So your PLC is not going to speak MQTT TLS, is probably not capable of doing a TLS handshake, and certainly it could be, but not really its sweet spot. So we have a problem there. So then we're behind the firewall. So that's where the protocol conversion process comes in. So we're going to take that Ethernet IP Modbus message and convert it into MQTT TLS, and we're going to take advantage of the fact that we probably have a service running somewhere in the building that already has access to the firewall in order to do your WMS software management of that device, and which could have cloud access, and that thing will work as a proxy. So the first thing, as we talked about earlier, is that communication. Your protocol conversion process can solve that communication. So now our light bulb, our industrial light bulb, our PLC can at least speak to the cloud. So that problem is solved. The next thing we've got to do is event persistence. So as I said, we're largely talking about event-driven processes. So some event happens, react to it. Some event happens, react to it. Perfectly reasonable to do that. And so your protocol converter could just, instead of sending things to MQTT, or in addition to sending things to MQTT, you could just send things to SNS or SQS or to any other mechanism of getting them to the cloud, right? You can just have a little proxy there that gets the messages in and out. It doesn't have to be IoT. We thought there were some particular advantages in IoT, and IoT had this shadow object, and so how would we use the shadow? And initially we sort of thought of it as a thought experiment almost, like how would we use the shadow? Like we're an event-driven process, but like let's think about that. So you don't have to be event-driven, right? You don't have to be state-driven, rather. You can be event-driven. And some things are better served as event-driven processes, like your time series data, your metrics coming out of the device. Those don't really model well going into a shadow. So if you're constantly changing state and you're trying to just record that in your time series data, that's probably just best served as going through your MQTT broker in this example, going into a rule that forwards it to Dynamo, forwards it to Redshift, forwards it to wherever you want it to be for your time series data, time stream, however you want it to get there, right? To a lambda that post-processes it, IoT analytics. There's a lot of ways you can do that depending on how you want to consume the data, right? And so that's not a great use case for state updates. And another one that's not a great use case necessarily is there are Workcells that have fairly high transactions per second, fairly high decision-making processes that are time sensitive. And they're not really what I would consider a discrete, or finite state machine that's going to converge, stay in a particular state, wait for an event, and then transition states. It's in a state for a very fixed amount of time, and then it's going to change, right? So you think about the difference between like an elevator and an escalator. An elevator hits discrete states and stops, sort of floor to floor. An escalator is always in a meaningful, useful state at any given point. Like, there's not, how would you define like move from here to there? It's more just like spin, right? Turn. And so while you could model an escalator probably as a finite state machine with a shadow, I'm not saying you couldn't or it wouldn't be reasonable. I'm just trying to give some metaphors there. Similarly, in the industrial scenario, maybe a high-speed conveyor sorter may not be well modeled as a finite state machine using a shadow. You can still use events for that. So, as I said, not all things are modeled well as with a shadow, but our Workcell is. You saw the tote shows up, it sits at that infeed, the robot sits there, waits for a command, moves it, rinse and repeat. So it's there, follows a finite state model very well, and so we ended up using the shadow, and we'll go through that. Am I moving? So why separate the protocol conversion and the event persistence? We could have put this event persistence layer, this convert to a shadow basically, in the protocol converter layer itself. We could have said, do it all in one bundle, right? We didn't do that for two reasons. The first one was because we weren't really sure which of these we were going to keep as we were going through the process, so we wanted to kind of be loose about we were pretty sure about the protocol conversion need, right? Need to get things to the cloud, but weren't so sure about this shadow mechanism, so we were kind of being somewhat non-committal on that, and by splitting them into different processes and having a microservice-based architecture, that allowed us to decouple those decisions. We can go from event persistence to making an event handler. So that was one reason. But a more important reason was that we wanted to make the device look native, like it was a native IoT device out of the box. And so by building this protocol converter facade, it made it look as though this device could already speak MQTT-LS. Then, the event persistence layer gave us an opportunity to make the device look like it was just doing shadow updates. So if I had a PLC that was capable of just emitting certain state to the cloud as a shadow update, then I could throw away that code, in a sense, have a native industrial IoT device that could just replace that function, and all of my core business logic remained the same. And so separating those in that way was a useful paradigm for us. So another reason that we have this here is that we want to, as I alluded to earlier, we want to pull the brains out. We don't want to leave the brains in the PLC at the edge. We want to have that thinking being done in software. Not because software is particularly better for it, one programming language versus another, but because all of the power of AWS behind it. Because we can do continuous delivery, because we have access to all these incredible tools inside of AWS that we don't have down at the PLC environment. And so we want to make sure that we are optimizing the PLC for what it's good for, the safety, the integration with the industrial devices that it does, but not try to put too much burden onto it, not to overwhelm the PLC. Just let us focus on what it's really good at and put the other stuff elsewhere. Okay, so let's look at what I mean by translating. What is that protocol converter actually doing? So before we do that, let's think about the life of a tote. We have totes showing up in the system. They're going to arrive at an in-feed. That tote is going to get picked up from an in-feed, go from the conveyor to the arm. It's going to hold it, so there's a pick process there. And it's going to go from the arm to a pallet. And eventually that pallet's going to get full, and we're going to remove it. The tote exits the cell and goes on about its way. So sort of what a tote looks like going through the in-feed. So you can imagine that there's a number of different commands or events that happen in each of those things, and we could have break that move up into a number of different things. But let's just simplify this. Remember I said this is our hello world example. So tote arrives at an in-feed. This is what I think of as the industrial hello world model is. Tote shows up, scanned, tote leaves. Pretty simple. So let's do this hello world example. So this is what our arrival event looks like. We've got some custom protocol that I invented for the sake of this talk. We've got some comma-separated message stream format here, which we have an arrive event. This IFO1, which is some way of representing in-feed number 1, right? And we've got a barcode on that tote that shows up and a particular time that it got there. How could we model that as a state update? Well, we can turn this into a reported update into the shadow, turn that into an in-feed so it's maybe more readable. Put the barcode as the value in the key value pair, and that event has now been transformed into a persistent shadow update. It's going to be in there until another event triggers, maybe like a depart event, that would cause that to get emptied out. The time, we can either record that time in the shadow as well, or we can take advantage of the fact that the shadow has a metadata section and records time of when that field was last updated, up to you. Okay, that's how we convert it into a shadow update, but that's not what we were doing. That was the event persistence layer, right? So if we go back here, in this code, this is what's running. Oops, I'm going the wrong direction. That's what's running in our event persistence layer. So in the protocol converter layer, that's the part that's just translating from, in this case, a TCP custom protocol, unencrypted protocol up to an MQTT TLS secure handshake message. So we're going to take that payload, stuff it into a JSON field inside of a JSON envelope called payload, and give it some header information, maybe what cell it's coming from, maybe time of day it was generated, and some other metadata, whatever's appropriate, and we're going to emit that. And emitting it as a JSON object has some various advantages. Most notably, it lets us play inside of the rules engine. And then, so that's the message coming up. And so we want to send a message back down. We could do something like what I alluded to earlier with the light bulb case of a desired reported, so it was blue, we want to make it red. And say, okay, well the desired state is, we want the in-feed to be empty, and we want this destination to have the barcode. And so figure it out, Workcell, right? Infer it from these state transitions. But that's not really desirable for us for a couple of reasons, to leverage the desired state in that particular way. Because, well, first of all, it puts logic in the edge device, right? The Workcell now has to know, how do I do this inference? And as I said before, I really want to leave as much in the cloud as possible so I can take advantage of all this AWS goodness, right? So that's a problem. It also means that because it's in there, I'm not able to use an off-the-shelf product and to just plug it in, right? The device is now no longer just a commodity device. It's now something that has some brains and business logic and meaningful bits that I really don't want to touch. And so, which also means now because I've got that in the edge, I've now got to have an update and a management process for that block of code, right? And then lastly, and this one's more subtle, so I'll spend a bit on it. It's not something that's advantageous because doing these complex state transitions are problematic in that way, or can be problematic, I would say. So, and by an analogy, imagine we've got a bunch of baking ingredients sitting on a table and an oven sitting next to it. And I take all those baking ingredients, I just throw them into the oven, and I turn the oven dial to cake, right? That's my desired output is cake. Birthday cake, chocolate cake, your cake of choice. And as a consumer, as a customer, that's a pretty compelling scenario, right? And as an oven manufacturer, that might be a compelling idea because now I can produce these complex devices that really delight my customers. But as a baker, that's probably not the oven that I want to buy, right? It removes the opportunity for me to put my brand on it. It removes the opportunity for me to put my subject matter expertise into that cake, right? It removes the opportunity for me to problem solve. What if I make a mistake? I don't want to throw away my inventory and start over from scratch. I might take that failed cake and turn it into cupcakes or muffins or some kind of other special yummy treat that I'm going to be able to market to my customers, right? Similarly, if my Workcell makes a mistake halfway through, I may not want the edge device to make a decision because I can make a better decision, or I may make a different decision tomorrow. I may say, well, put it over here, and it fails. And I might say, today we'll just fault the cell, stop the presses, don't do anything, don't create bad work, fire an and on light, somebody come problem solve. But tomorrow I may change my mind and say, well, let's just put it somewhere so we can keep operating, right? And both may have good reasons from a business model to do that. And you may change your business model, business decision, say this is what we're going to do, or one building may be different than another one for different reasons. So embedding that logic in the edge means you're going to deal with all those problems. Leaving it in the cloud or in the software layer allows for us to make those updates quickly, but make sure that the cell is still safe, principally. So instead, we just send a message back. Same thing, it's just instead of going up, it's going down. Still have a header, still have a payload, but this is a down direction instead of an up. It's going to the device, to the Workcell, saying, do a move from infeed 1, move this barcode to this destination, something like that. So that's great, but what are the problems? That means that we can do all this stuff from the cloud. It's really cool. We're taking advantage of this IoT space. We're using the shadow. We're using rules. We're using lambdas. We can integrate with all these other systems like Dynamo and S3 and move data into Elasticsearch and Redshift and to Athena, and we were doing all of that. But what's the problem? Well, we've got a latency barrier now because we're going to the cloud. That's 50 milliseconds, 100 milliseconds. What's your P99? What's your round trip expectancy for these tote moves? We've got a bandwidth constraint. So if we're trying to push a really large amount of data up to the cloud, we're going to have a problem. And we've got connectivity issues. What if we go offline for a while? Do we want our cell to stop working? Do we want it to keep working? So talking about a use case, let's imagine that we want to add in a new device. We're going to kind of cover some of those. So we're going to take an off-the-shelf camera. We're going to add it in. And what this camera is going to do, it's going to sit at that infeed that we looked at in the beginning. And it's going to analyze those totes coming down for defects and see, are any of them going to cause a problem when I'm trying to place a tote? Because if I go and pick up that tote and it's damaged, I could maybe drop the tote. It could be a safety risk. I could maybe damage the end of arm tool effector on the arm, and that could be expensive. I could stop the operation. So I want to throw in this vision camera at the edge. Well, vision, probably going to be a lot of data. Probably going to have to make some high-level decisions. And how am I going to do this? So camera's going to come up and walk us through how we're going to use Greengrass to do this.
Thank you, Josh. My name is Cameron. Hi, everyone. Some background on myself. I've been at Amazon for about 4 years, and the kind of story that Josh is telling here with these changing requirements or adding new and interesting devices to our Workcell, this is something that I've seen time and time again, not just with the palletizer, but with any number of other Workcells that I've come across in the last 4 years. So just really speaks to sort of the pace of innovation that people should expect in the industrial space. So this new camera that we want to add into our Workcell is actually a real scenario. There are definitely use cases that we had some engineers looking at to say, hey, can we take an off-the-shelf computer vision system, look at a stack of totes, a stack of containers, and tell how many are there on that pallet, or are they tipping over, and maybe some of them have fallen over, and it's creating sort of an unsafe setup for the Workcell, and it shouldn't be able to operate on it. So Turns out, yes, you can do stuff like that with modern computer vision systems and algorithms, and that shouldn't be any surprise. These things keep evolving, becoming more and more sophisticated, and there should be no reason as an industrial automation owner that you can't take full advantage of that and start evolving your industrial automation at the same pace of all of these wonderful devices and software techniques. So I think Josh probably alluded to this, but can we see, why don't we connect this new modern computer vision system to our PLC? Great, except for one thing. PLCs are industrial devices and don't always have full connectivity with the whole variety of off-the-shelf devices that you have at your disposal. So unfortunately, we're not able to make that connection. And even if we could, the software engineers that I work with don't know how to write ladder logic to run their computer vision algorithms. They're used to using more, commonly available software languages that they're familiar with. What about the cloud? Could we connect this computer vision system to the cloud? Perhaps, right? You can imagine that there's at least some way that you could even provide some proxy or some connectivity option to get that camera data up to the cloud. Certainly, there are people working on solving these problems. If we did that, however, we would be paying quite a cost in terms of latency and bandwidth to send all of that image data up to the cloud, process it to make some decision, and then send back a result back down to your edge. So that wasn't really a viable option for us either. We wanted something that was going to be responsive and fast, and we could build in some sophistication close to the edge. And that's really where we started to look at Greengrass as an option to let us extend our software stack from the cloud down to the edge, co-located with our industrial equipment. So here we have our Greengrass control logic layer now in between the IoT cloud layer and your devices. So the Greengrass control layer is located on an industrial PC, sitting next to or very close to your equipment. In this case, we have it connected directly to our PLC and the computer vision system. So let's zoom in and take a look at what's inside this Greengrass control layer. For those of you who are familiar with Greengrass, it's definitely probably not surprising that inside your Greengrass layer you have lambdas, right? So everyone here has probably heard of lambdas before, certainly in the context of running lambdas in the cloud. Same idea here. You define these lambdas and they have a main sort of message handler as their main entry point. However, there's one key distinction in the way that we configure our lambdas for our Greengrass control layer here. We configure them to run in a pinned mode or a long-lived mode, and this is a bit different from the on-demand sort of scalable lambdas that you're used to in sort of the serverless cloud architecture. You can do this in Greengrass to set them up to be scalable in an on-demand fashion, but we configure these ones as long-lived lambdas, and what that means is that the Greengrass system is going to instantiate one and only one process for each of your lambdas, and keep that process running as long as it possibly can, so that it's not designed to scale. And one of the main reasons that we're doing this is that the lambdas that you see on the bottom of that box are maintaining a persistent single connection to their respective devices. So these are what I would call device adapters or device adapter lambdas. So on the left you have a computer vision lambda that is maintaining a persistent connection to the camera system. And on the right you have a PLC lambda, similarly maintaining a persistent socket-based connection to this PLC system. Josh has used the term Ethernet IP. If you haven't heard of that, it's basically Ethernet IP is a kind of a misleading name, but it's a very specific industrial protocol. Ethernet industrial protocol is what we mean by Ethernet IP, and that happens to be the socket connection there between the PLC lambda and the actual industrial controller. In the center of both of these, we have something that we are calling the Orchestrator lambda, and what we mean by that is that this is sort of where we're centralizing the decision making, the business logic, the workflows, whatever you would like to call it, in the Greengrass layer here running at the edge. So essentially this is a hub and spoke model that we've implemented in this particular architecture. There are certainly many other ways that you can connect or design your lambdas to run in Greengrass, but this is the pattern that we're going to be using for today's topic. So as an example of Josh's tote lifecycle, let's go through what this would look like in the Greengrass domain. A tote will arrive, and what happens is the PLC will make some change, or its state will change because there's something new arriving at the conveyor at the Workcell, and the PLC lambda is going to pick up on that change and notify the orchestrator that a new tote has arrived to be processed. The orchestrator is then going to communicate over to our computer vision lambda to capture some images, perform some computer vision algorithms, and determine, hey, is this tote a good one? Is the pallet in a good state? Maybe the tote is cracked, or maybe somebody accidentally sent down a box or another package that's not the right form factor for this Workcell. So let's use our computer vision system now to help solve those problems and take a look. And then finally, the orchestrator is going to decide, well, given all of that information, what do I want to do with it? Should I actually move that tote or perform some other exception handling routine? So these messages that I showed sort of flowing between the lambdas, we've basically modeled them as two kind of distinct types of messages that we happen to like when we're modeling inter-lambda communications at the Greengrass layer, events and commands. An event message in this context is really just a single direction message sent from one lambda to another with no expectation of a response. This is very common and typically done as a result of some state change in your device. So on top here, we're seeing, the PLC is constantly changing state and it's updating its internal state. Our PLC lambda is talking the device-specific protocol to read that state change and essentially transforming that device-specific information into some object model that you're using to represent that as an event and send it to the orchestrator so that it can consume that information and make some intelligent decision. The orchestrator is then going to say, okay, now that I have that information, I probably want to do something with it, so I'm going to then send a command to the computer vision lambda, and the command is made up of a request and response message. So when I'm using these terms, events and commands, that's really sort of just the modeling that we're layering on top of the messages passing between lambdas. An event is the fire and forget single direction message, and a command is a request response style message. I'll also just make a note here that this is sort of one of the ways that we're finding it useful to think about these device lambdas is that they're doing a very good job of just adapting your industrial device or your computer vision system, whatever device you have at the edge, from its own specific native protocol that might be very specific to that one device or that one manufacturer. And it's translating it on the other side into some service model that you're defining using, standard software languages that you're familiar with. So the practice of just defining your service model, how your service is going to emit events and respond to operation requests and responses, using all those sort of standardized ways of modeling a service, you can apply those to your Greengrass lambdas and kind of abstract that device-specific interface and device-specific protocol. So if I had a computer vision system from Acme today, that could conform to a service model that I define, and then tomorrow I get a computer vision system from Acme's competitor, and I interface to that device, but I maintain the same sort of service model on the Greengrass side so that it all sort of fits the same patterns. So let's go one level deeper and look at actually the very lowest level that we can get to in terms of what this tote arrival actually means when we're looking at the signals from the PLC into our Greengrass layer software. If you're not familiar with these devices, I'll try to sort of describe them a little bit, but they're really not super complicated. There's a ton of devices inside your Workcell that's connected to your PLC. One of the most common ones is called a photo eye. And all that is it's a very, very simple optical sensor whose job it is to tell you when something is obstructing it or not. So it's just a very simple binary sensor, either true, it's being obstructed, or false, there's nothing obstructing it. And certainly there are many of these in our Workcell. In particular, there's one at the main in-feed conveyor of the Workcell, so that essentially is going to tell us when there's a new tote that's sitting there. So an item arrives on the conveyor, and our photo eye is going to emit a 24-volt signal to indicate that it's currently obstructed by this tote sitting there in front of it at the conveyor. The PLC takes that 24-volt signal into its input module, and it's going to do some filtering on the signal. Perhaps you're applying some simple debouncing logic to that 24-volt input signal. And the PLC is going to then store this in some sort of state variable, or a tag, as they're called in PLC terminology, called item present. So the PLC is taking a raw voltage signal over a wire in its input module, and assigning it now some stateful meaning to say, hey, there's an item present, true, there's something there, or false, there's nothing there. Our PLC lambda is in constant communication and has a persistent connection to the PLC. And it's using the Ethernet IP industrial protocol to periodically scrape the values of many state variables inside the PLC, one of which is this item present tag. And so the PLC lambda is doing this in the background on sort of a polling thread. And when the PLC lambda detects that this state variable, item present, is changed from false to true, that means that there's something new that's happening at the Workcell, and I should construct a new item arrived event and pass that along to the orchestrator so that it can make some informed decision about what to do with that information. So there it is, sort of translating from the 24-volt signal over our industrial protocol, and finally, being emitted as a standard sort of object item arrived event in the Greengrass layer. So how do we actually do that in Greengrass? Well, we need a couple of pieces of simple information to construct this event. One, we need the orchestrator ARN, the Amazon resource name, so that the PLC lambda can target that message to the orchestrator. And we need the value of our item present tag. So here I'm just sort of simplifying and showing, we have an Ethernet IP client that we're using to read the value of that tag, and we're monitoring it. And when it changes, we build a new item arrived event, and then we're going to call a method send message async to the orchestrator to send that information, that item arrived event, to the orchestrator. So what is send message async doing then? Let's go one level deeper. Send message async is taking in your ARN, which is the recipient of your message, and it's taking in an object that represents your message. And the first thing that we do is we serialize it. So in this case, we're taking our message and we're using whatever your favorite serialization library is to take the object and serialize it into a JSON string. And we begin to build our invoke request that we're going to use to send through Greengrass to the orchestrator. The invoke request gets built with something called a client context here. That's a completely optional step, but I'll explain why we're using it here. At the top of this code snippet, I have a little bit of a description of this static message context that we're attaching here. And all that is really, it's an opportunity for you to add some JSON formatted metadata into your message before you're sending it over to the recipient. So in this case, I've decided, sure, let me add some metadata to my message. I'm going to set some custom attribute, is message, and a value true. And what this is going to be used for, we'll see on the receiving end, is we can use that information and use that metadata to determine something about the message and handle it in one way or another. So we build up our message context and attach that into our invocation request. We set the destination ARN, so who's going to receive the message, and the payload that we've serialized, we add that to the request. And we also set an invocation type. The invocation type that we're using is event. There are two different types that you can use, event or request response. If we had used the request response type of invocation type, what would happen is we would go to invoke that request, and this thread would block. And everything would block until the recipient had processed and sent you a reply to that message. In this case, as I said, we don't want or expect any kind of response from this event. We're simply translating that state change into an event, and we want to fire and forget and send it over to our orchestrator. So accordingly, we're using the invocation type of event so that we're not blocking. And finally, we use our Lambda client from the Greengrass SDK to send this request. And we're done. The polling thread continues in the background and continues looking for interesting state changes to then translate and send up to the orchestrator. On the receiving side, the orchestrator is going to have its main Lambda handler method defined, just like you do with any Lambdas that you create in AWS. And that handler here has an input stream, an output stream, and a context object. And I think you might guess that the context object is indeed going to contain that metadata that we had set when we were constructing our message. So the first thing we do in our message handler is we check that context and check for that custom attribute which we had set and see, hey, is this a message that I recognize? Do I know how to handle this message? Can I safely deserialize it? And indeed, yes, we do know this type of message, so let's go ahead and use our object mapper, whatever serialization tool of choice, and deserialize the input stream back into a message object that you can then handle in your software layer and pass it off to some message handler. And if you're looking closely enough, you'll see that I'm using something that looks like message handler dot handle message async. And sort of the reason that I'm putting that there is that this is something that we found to be a very useful pattern. So kind of a tip or something that we found to be particularly useful is that when we are using these long-running lambdas in Greengrass, we typically have some cases where these messages might kick off a long-running process. This event could be, something simple that maybe is just, being handled by emitting a metric or updating some state model, or it could be an event that means, I need to communicate with cloud services, I need to move a robot, I need to do some long-running process that's going to involve machinery, and it could take many seconds or minutes even. So if I were to do that synchronously, right here where I receive the message, I would effectively be blocking this Lambda handler thread. As a pinned Lambda, this is your single point of entry, single-threaded message handler for your pinned Lambda. So if you block this thread, you're essentially stopping any new messages from getting processed. And ultimately, if you're taking too long, Greengrass might ultimately terminate the process and attempt to recover and restart your long-running Lambda because nothing was getting through. So first thing that we do, just as a matter of practice, as a pattern, is we get the message and we, as soon as possible, pass it off to a background handler, which you can then use to dispatch the message or queue it or handle it with whatever sort of concurrency model you'd like. But keep this thread free and unblocked is sort of the useful sort of pattern that we've found. So once we've actually gotten that information to the orchestrator is going to decide, okay, now let's make some decision. Maybe I've verified with Josh's IoT application that this is a good tote, and we've decided to move the tote. So I'm going to send that command to the PLC, and then the PLC is going to do actually a whole sequence of things. There's no easy way to move a tote really with industrial equipment. There's a whole lot of steps that are involved. The PLC's got to receive this command. It's got to check a myriad of different sensors, updating some UIs or HMI displays. It's constantly monitoring safety systems to make sure everything is in a safe operating mode. And maybe it's triggering barcode scanners and eventually moving robotics, motors, and actuators. And at the end of it all, it's going to just determine how to respond to this command and tell you whether it succeeded or failed at the end of it. So that's it. You're done. You've moved a tote, and you're never, ever going to want to change that logic, right? Right. Yeah, right. So just like everything else, the story here is you want to be able to change this logic in the same ways that you want to change any of your logic that you own in your traditional software systems, right? There's always opportunities for either improving your logic, adding monitoring capabilities, debugging, metrics, certainly fixing bugs or issues that you're encountering in the field. Industrial logic is logic that's fallible too. There are bugs that happen. And then even if there aren't bugs, there are ways that you might want to repurpose this or pivot this logic for new applications or for new interesting exception handling capabilities that you want to just improve the performance of your Workcell. So we found doing this inside of the PLC layer to be somewhat intractable in the sense that, A, we don't have the domain expertise among the software engineers to actually manipulate this logic as well as we do our software logic. And B, the sort of change cycles involved in updating industrial equipment and industrial logic and how do you test that and everything is much, much different than what we're used to working with in the software realm. So how can we, again, leverage Greengrass to sort of improve this situation so we get back to something where we can start iterating more quickly and with more confidence? Well, in the same way that we added a device lambda for a camera system, a computer vision lambda, we can also start thinking about constructing individual device lambdas that now integrate with our robotics, our UIs and displays, our barcode scanners, any other local device that you can sort of connect to over Ethernet or serial or other protocols. You can imagine constructing a device adapter lambda whose job it is to now integrate with that device and hook back into your orchestration layer in the software stack that you own. And what that really lets you do is now take some of that logic that was previously in the PLC ladder logic and move it up into your software layer. And this does not eliminate the PLC. I think Josh was mentioning this as well, is that the PLC really is very good at sensor integration, high rate control, filtering and debouncing, and most importantly, the safety logic, the safety critical certified safety systems that are required to make sure that you can actually run your Workcell in a safe manner and that the people that operate the Workcell are safe. So the goal here is not to replace the PLC with software logic, it's to augment the PLC and let the PLC focus and really hone in on its core competencies and play to its strengths as much as we can and leverage the software side in the Greengrass layer and above to leverage its strengths, which is really owning the business logic, owning some coordination logic that you can modify, you can instrument, and you can use all the best continuous deployment practices that you're familiar with from running software. So to summarize our journey, sort of where we started with an IoT core application that was connected to a single PLC as sort of the main entry point for all of the devices in your Workcell. We added a Greengrass layer, which then let us add new devices like computer vision systems. And then we didn't stop there. We had more device lambdas, which then let us further decompose our device connectivity into all the different devices and let us sort of leverage software now to move some of that logic up out of our industrial controller and into a Greengrass layer and really make the most of the software that we have running at the edge. This is a very simplified architecture of some of the AWS services and tools that we're using in this kind of an architecture. There are certainly many, many more. I'm not going to list all of the various AWS tools that you could possibly integrate in these layers, but there are plenty. And I hope that some of these patterns and ideas were useful to you, or at least get you thinking in a different direction when it comes to industrial automation and how you can manage that with some AWS tools. So with that, I will invite Rudy to come up for some closing remarks.
Cool. Well, you know what? I'll say thank you to Josh and Cameron for sharing their story. And for those of you who are still keen to continue your IoT journey, here's some resources that you can check out. The Amazon Day One blog. We've also got a track and trace solution that we've made a video about, and also an IoT workshop. So if you want to actually get into it and do an IoT 100 level workshop, if you've never done that, you get an ESP32 microcontroller. You can buy those online. You utilize AWS IoT Core, so you'll connect the device to it, and then you'll provision a lambda function which will be triggered with a fake event. In this case, like I said, a temperature spike, and then you'll get a notification by plugging in SNS to either send you an email or an SMS message. And with that, I'll also say, please check out AWS training. Training and certification. I mean, you can learn a lot of IoT, or at least about AWS IoT there, and you can see from the core to Greengrass, analytics, even device management. And with that, I'll say thank you for joining us, and since we're out of time, if you want to have, or if you have any questions, we'll take them outside in the hall. But thank you for joining us.